Fermentation of sugars to ethanol has been a common human festivity since humanoids first ingested overripe berries. Today, a vintner creating the next great Cabernet, as well as an engineer processing biomass, employs the fungus brewer's yeast to convert glucose or fructose in plant juices to ethanol. This reaction proceeds until ethanol concentrations reach between 14% and 15.5% by volume, the upper limit of the tolerance for the yeast. After fermentation, the moonshiner, vintner, brewer, or engineer distills the liquid to remove water and produce nearly pure ethanol. Distillation separates chemicals by their differences in boiling temperature. First, the fermentation solution, or mash, is heated in a still to above 78 degrees Celsius, the boiling point of ethanol, but below 100 degrees Celsius, the boiling point of water. Ethanol vapors rise to the top of the still, where they cool and condense into a liquid again. Finally, the distillate collects in a holding tank. Stills designed for biofuels produce a distillate that is up to 95.6% ethanol and as little as 4.4% water. The last step of bioethanol production is dehydration. The most common method is to pass the distillate through a molecular sieve that absorbs the remaining water. A molecular sieve is a material like aluminosilicate clay with pores large enough to trap water molecules but too small for ethanol molecules. The end product of these dehydration methods is 99% or higher ethanol, ready for combustion. The processes of sugar extraction from plant biomass, fermentation of sugars, and distillation and dehydration of the ethanol have an overall efficiency of about 87% in terms of the energy content of the ethanol produced over the initial sugar in the sugar cane or sugar beet. Starch is a polymer of glucose sugar, meaning that it is composed of many glucose molecules linked together in a chain. Plants store starch instead of sugars because it is less susceptible to pathogens and presents a more favorable water balance because it acts as one osmotic unit instead of many. Maize kernels, for example, contain about 71% starch and only 1 to 3% simple sugars. Conversion of maize kernels into ethanol begins with milling. Hydrolysis of starch is the next step in maize biofuels production. During hydrolysis, enzymes break down starch into its glucose subunits. Once hydrolysis is complete, yeast are added to ferment the glucose syrup to 10% ethanol or higher. Fermentation followed by distillation and dehydration results in a product that is better than 99% ethanol. Processing maize kernels to ethanol is less efficient than processing sugarcane because of the extra steps involved in converting starch to sugar. Starch extraction from the plant biomass, hydrolysis of starch to sugar, fermentation of the sugars, and distillation and dehydration of the ethanol has an efficiency of about 66% in terms of energy in the final product versus energy in the original kernel.